Alright, so in this video we'll be proving the Laguerre polynomial. So we have a function to be e raised to power minus st over 1 minus t, all divided by 1 minus t. So ln of x or lx is given as that. So this is a Laguerre polynomial. So we have to prove this. Now we start proving from recall from Taylor series that e raised to power s is the summand of s raised to power n over n factorial. So there is an implication that x is equals to 1, s equals to minus st divided by 1 minus t. So clearly you can see that x e raised to, we have e raised to power x, so this simply means in likewise manner we have it to be, we have our x to be minus st over 1 minus t. So when we substitute it back, we have 1 over 1 minus t. In fact, the left hand side can still be written as 1 over 1 minus t summand of 1 over n factorial, since the Taylor series is written as s raised to power n over n factorial. So anywhere we see x, we are inserting minus st over 1 minus t raised to power n. Then when we open the bracket, we have minus 1 raised to power n over n factorial 1 minus t raised to power n plus 1. The n plus 1 is coming from the left hand side. The 1 minus t that we have as the denominator is added to the other one, so we have raised to power n plus 1. Then we open the brackets to be x raised to power n, t raised to power n. So we recall from Taylor series that 1 minus t raised to power minus r is given as the expression above. So of course, to generalize that expression, we have it to be r plus 1 up to r plus k minus 1 t raised to power k over k factorial. Then we introduce r minus 1 factorial over r minus 1 factorial. The r minus 1 factorial can cancel each other, so it's just an introduction. So when we multiply it with the initial condition of r plus 1, everything becomes r plus k minus 1 factorial, such that when you inserted the value for k to be 0, you will still arrive at the expression above. So that is it. So we compare 1 minus t raised to power minus r with 1 minus t raised to power minus n plus 1 from the previous image. So we have our r to be n plus 1. So we are substituting the value for r to be n plus 1. Then we have 1 minus t raised to power minus nt plus 1 to be equals to n plus k factorial over n factorial k factorial, all raised to power tk. So that's expression 3. So we have our expression 3 there. Then when we substitute it back in equation 3, we only look for the value for 1 minus t raised to power minus n plus t. So on substituting it back, we have it to be summand of summand, r equals to 0, k equals to 0, then n plus ks raised to power n, t raised to power k. So let's represent that equation as Iseyon. Then comparing Iseyon with ln of x, we replace n equals to n minus k, such that the summand of, we have two different summand, the first summation, and so we compare Iseyon with the normal equation of for Laguerre, that's n plus k, n equals to n minus k, such that everywhere we see n, we are representing it with n minus k, t raised to power n minus k. Then since we are trying to manipulate our final solution to that of a Laguerre solution, we introduce, initially we are having n factorial, then we can write it to be n factorial all squared over n factorial, such that when one of the n factorial cancels out, it goes back to its initial pattern. Then we factorize, we bring out c raised to power n over n factorial, where all the expression is representing the generating function for Laguerre. So we have it to be summand of lnx t raised to power n over n factorial. So this is the proof for that very question.